Next speaker is Professor Da Yan from Tsinghua University. So I'm very honored to introduce Professor Da Yan. Professor Da Yan is a tenured professor at School of Architecture, Tsinghua University. Since 2005, Professor Da Yan has made significant original contributions across a diverse set of research areas and projects. His research focuses on energy efficiency of buildings in 3 areas. Number 1, development of building performance simulation toolkits, which is known as DEST. Number 2, research on occupants' energy-related behaviors in buildings. Number 3, research on building energy consumption model of China and low carbon and energy saving related policies. So based on the above research aspects, Professor Da Yan has published over 200 papers, more than 10 books and reports, and applied over 10 patents and software copyrights. And he serves as the editor-in-chief of Journal of Building Simulation, which is the first SCI journal in the field of building simulation all over the world. And in 2019, he was rewarded the title as FIBPSA Fellow. He was awarded Best Review Paper of Journal of Energy and Buildings in 2018 and highly cited paper award of building simulation in 2017. So now let's welcome Professor Da Yan to give a talk. His title, speech title is A Novel Approach to Generating Typical Building Electricity, Use Profiles for Renewable Energy System Design and Smart Grid Integration. Please, Professor Da Yan, the floor is yours.
Thank you, Bing, for your very kind invitation and also introduction. It's my great pleasure to have the chance to introduce my work to all the audience. And also it's a great pleasure to have the speech after Professor Kang, after his very outstanding presentation. So today I would like to show my undergoing research topic about a novel approach to generating and also forecasting building electricity use profile, especially for the renewable energy system, for design and also smart grid integration. So the building sectors using around 30 of the total energy consumption and also another 30 of total carbon emission in the world. Many of our countries have a set of very ambitious targets for the carbon neutrality. So this gives us quite a lot of work to do the research. And by the developing and the implementation of renewable energy devices like the PV panel, wind power, hydro power, one of the a very big issue for us is try to balance the supply side with the demand side. In previous work, mainly the work is driven by the supply side, try to using the diverse of the dynamic supply for the demand. But when the situation changed greatly and greatly, like the dark chart, this is a very famous chart to show when the more and more renewable energy has been implemented. So there's the change so greatly that the supply side and demand side should be cooperate with each other to make a balance between each other. So based on this very big background, we would like to say how to do this job. It's very necessary to understanding the features and the characteristics of building building electricity usage, and also in the design phase and also for the operation phase. So this is if you know the situation and also the key parameters and the features of this building and electricity usage, we can better to for the BIPV system design, and also it's very necessary for the battery management and also demand side management. So how to do this job? There's two kind of model. One kind of model is we call the electricity profile model. The electricity profile model, from my point of view, is trying to facing the design phase, try to identify the statistical characteristic of the energy usage for the building sectors for whole very long period, like a whole year. And another very big part of the model is the prediction model. This model is more focused on one specified object, like a building or district or urban, and focus on the real operation data. And the key issue is try to more accurately reflect the real energy uses in the future, in the next very short period, like 1 day, 24 hours, or 1 month, for instance. So if we compared with the weather data, so the forecast data is more like the weather forecasting. So it's try to identify and forecast the next day what will happen. And for the profile model, is try to analysis the 30 years of data, weather data, try to generate one typical year of data, using this as one design phase reference that try to identify how the local climate data will affect on the building. So that is very different. Two part of this, two types of the models we needed to do. Sorry. So among these all factors affect building energy consumption, another very important issue is behavior. So what kind of people we are living inside the building is also significantly impacted on the building indoor environment data and also energy performance. So it's also very necessary to generate a typical pattern for the occupancy profile inside the building, and also in some case we need to predict how many people will be inside the building in the next day for the 22 hours. So that is very helpful for the building design and also building electricity usage predictions. So this research objectives is try to develop 4 models. One model is a profile model for the occupant behavior, especially for the occupancy profile. Another is to try to identify and forecasting the next day's how many people will be inside the building. It's an occupancy prediction model. And based on this occupancy model, we can generate and create the electricity use typical electricity profile model and also electricity prediction model. So this is the 4 targets we would like to set. And firstly, I would like to try to introduce our typical occupancy profile model. The occupancy profile model is a series of occupant members in a room or in a zone or the whole building, or in the whole city sometimes. So it's quite essential for the design period to estimate and using that as an input for the energy system optimization, and also how we can optimize the building fabric and also building technology. So before, we mainly using the questionnaire or on-site environment to test how many people will be inside the room. But now using quite a lot of big data, we can collect through some social media and also some mobile position data. We can easily to collect quite a lot of data from this big data set. So we select using the Tencent, which one is a very famous international internet company in China, try to get some location-based service data. Using this, we use the mobile position data, occupant members data in the building for 16 cases, which including several railway stations and some airport in Shanghai and also in Beijing. And we can use this as a very fundamental database to do the occupancy data profile generating work. So the time span is from the 2015 to 2017, totally 2 years of data in total. So we simply using a cluster analysis for typical daily occupancy profile generating. In the hospital case, 2 typical daily occupancy profile has been generated. For instance, this is mainly reflects the weekend and holidays profile of occupancy, and the cluster 1 is the mainly the weekdays profile. It looks maybe almost the same, but if we look at the whole week profile, we can see that in the on Monday is the peak occupancy status in the whole week, and in the weekend that's where we have much less people than the weekday, and especially we can say that they have a very significant decrease of the peak from the Monday to Friday. That is a very interesting phenomenon we can see from this big data. So based on this kind of approach, we can generate the typical profile of the railway station 1, 2, 3, and 4. You can see that it's the typical profile, so quite diverse from each other. Especially this one, station 3. This is a normal, we say normal speed is a low speed railway station. Compared with the other 3, the high speed railway station, we can just before because the high speed railway train will stop around 11 o'clock p.m. From the railway station, so the people will decrease. People's number will decrease very significantly after 11 p.m. But for the normal speed railway station, they will be continuously working and operate through the until very middle night. So that is what generate create very different patterns for the different type of the railway station. And if you look at the airport, there's almost the same in the big airport. But if we have the data for the small airport like branch airport, the typical pattern is so different. And also we can compare the commercial complex, that's including the shopping mall and also office building together. We can say that normally have 2 peak or 1 peak. Is mainly on the lunchtime and the dinner time. It's very different from the operation mode of this commercial complex. And if we compare our generate the pattern with the our current like the R3 standard, we can see the typical pattern is very different, especially for this hospital occupancy pattern. And we see that the very significant difference is in the middle night, there's still around 20 or 10% of the people still inside the hospital, and the peak load in the lunchtime is even higher than the R3 typical patterns. So that is where driving the building design and also sizing issues were quite different. So we can compare the result by using the conventional pattern with our current data-driven pattern. There's a very like around 10% of the cooling load total energy consumption difference, and also around 5% of the peak load diverse. So based on this typical occupancy profile generating work, we're using quite a lot of data from the cell phone and mobility data to generate the typical occupancy profile of the airport, railway station, and also some commercial buildings. So we can compare this with our very widely used conversational data. We can using this new profile to upgrade our current design profile, make our design more close with the reality. So based on this work, we sometimes necessary to forecasting the future 1 day, 24 hours of how many people will be inside the room. That will be very helpful for us to estimate how the air conditioning system will be used and how we can forecasting the air conditioning cooling load and some how we can adjust the setting point for the terminals. So this approach is a little bit different compared with the typical pattern generation, because we are needed to using the cross to firstly try to select the and analysis the key characteristic and also the statistical characteristic of the data of the occupancy. Try to using this to analysis the phenomena and the principle inside for the occupancy profile, and then we use this as one principle inside to establish our model to forecast the next 24 hours of how many people were inside the room. So that is it's a very interesting approach. It's different from the previous occupancy profile generating module. Firstly, we needed to collect the data like the previous work do, and we collect as more data as possible, and using this to generate the typical profile. Like we analyze this to specify how this is the key driving force for the profile has been determined to figure out what are the key issues we will change the profile. And then based on these key features, and we can extract this key feature from some machine learning method to generate the time series features. And we got the feature, then we can set up one machine learning method to forecasting the next day's data. Based on this, we can also using the evaluation approach to analyze the accuracy of this forecasting module. So here we're using the same data set, including the railway station, airport, and the commercial complex and hospital. And the time resolution is 1 hour. And based on this data, we first is standardization of the data. We're using the absolute maximum value way to standardization the whole data, and we also use the k-means clustering to cluster the whole data. And here we get the two profile like the previous instruction, and in this we can we analyze the key issues is the weekday and the weekend. And also use a typical profile for the different building, especially for the railway station, airport, and also like the commercial building and the hospital. And here we found that the very important phenomena or the features for the occupancy data is the occupancy numbers of building of the number in building is very time relative. That means the people's numbers will not be changed so significant during a day. So if the last the previous hour the people is quite high, in this hour in the current hours current time the occupancy number will be also have a very high possibility, that's very high. So that is driving us try to using the time series analysis to get the ACF and PACF to analysis the time relation, also time correlation between the different time steps. So in this kind of research, we can say if we lack 1 day, 2 day, that means 24 hours and 48 hours and 72 hours will have a higher relationship, can connect with the current time step. So based on this, we using the SRIMA analysis to scratch the feature from this time series data. This is a seasonal auto regression integrated moving average method. Using this, we can find the time step which we can have very strongly correlation with the current time step. Based on this, we can get the key input parameter from the time series analysis. We can integrate the correlated history time step with the machine learning method to estimate the next 24 hours of the occupancy numbers in the building. So in the model evaluation part, we compared with some very famous baseline model like a horizontal model, SRIMA model, and also ANN model, and also radium forest model. So and also using this, we can using the test data to consider the time relevance, and also as compared with our model and also the baseline model to say how is the accuracy compared with the real measured data for in the test case. So here we can say that in the all 16 cases, we're using the CVIMC as the evaluation criteria compared with the baseline model and our proposed SRIMA plus ANN model. We can say the baseline model is around 23% of the errors, and our model currently is 9.5% of accuracy. So it errors. So that is we can say that the new module can be much more accurate compared with the reference module. So in this kind of research, we say that the occupancy prediction is one a new topic that we are mostly focused on this augmented behavior model, cooling load usage or the electricity load usage, and to do the feature analysis. Then we're using the machine learning method to training the model and optimize the model. The key features is the structure of the machine learning module, and also the algorithm, and also the input parameters, and also the training data size. And last one, we need to do the model evaluation to say if this model is applicable enough for the real application. Here we set up the one case in using the temperature, humidity, and wind speed, and also current data of the weather forecasting as input for the machine learning module, and the output is the cooling load estimation. And also we can also use this model to generate the electricity usage for the next 24 hours. And this building is in Beijing. It's a very large commercial complex. It's around 85,000 square meters for the commercial part, and also 56,000 square meters for the office part. We forecasting the load from the March to September in 2020. So the model training optimization part, we optimize the model structure, predicting algorithm, and also input parameters combination, and also training data size. We using the grid search with the tenfold cross validation to optimize the module, and we can see the accuracy will be significantly improved during this optimization process. So finally, we got the predict model separately. If we can compare the using the total model to forecasting the total electricity usage of this building, or you can do this calculation separately. We will do the comparison. That's using if we individually forecasting the commercial part and the office building part will be much more accurate. And also the algorithm part, we select the XGB module for the machine learning module. And also here we think by the analysis of the wind speed is not so significantly influenced on the simulation result. And also we using 30 days as the input training data sets. So based on this, we generated the model, and we reduced the prediction error from 17 to around 12% of a proposed module. Based on this, we can we implement in that building, especially for the ice storage systems, and we can reduce around 25% of the electricity usage in the case building in 2020. So sometimes in this days one case studies, we can say because they have two peak electricity price hours. By using if you using conventional control strategy, we afraid that we will use out of the ice in the next few hours. So in these 2 hours, we're using the chiller to provide cooling. But if you have very accurate estimation of for the whole days of the cooling load, we can using this ice storage ice to provide cooling in that hour to reduce the electricity usage. So that's one very effective way to do this electricity usage optimization and also load flexibility analysis. So that's very interesting to do the load prediction work for the next 24 hours. Here we normally using the machine learning approach to do this, but it's very sensitive to do the input parameters and also kind of the structure of the machine learning model that will be used. And also we necessary to use a very carefully validation work to improve the accuracy of the prediction model. So based on this 4 parts of work, we developed, validated, and also applied the 4 models in the building energy electricity analysis, including the people's numbers in the building and also electricity usage. And from the model type part, one part is for the typical profile module. Another one is the more like a prediction model for to predict another 24 hours usage of the electricity usage of the whole people numbers. So as one conclusion, to understand the feature and the characteristic of the building electricity usage, it's a very interesting and also essential work to balance the design and also the planning of building in energy systems. We can see how the capacity of the battery and how we can provide the flexibility to this grid. And this study developed a series of the new approach to generate and predict the building occupancy and also electricity usage profile, and also to support the advanced building and optimization control of building energy systems. And also we starting to do some work of the forecasting model to analysis to forecast the data, energy data we would use in the next 24 hours. It's short time step of the forecasting work. So this is a totally new field, and quite a lot of people are working in this field, and still quite a lot of potential we can achieve, I believe. So we welcome everybody to join this and have more question and discussion on this field. That's the major part for my presentation. Thank you for your attention. And by the way, I would like to also promote our building simulation journal. An international journal is mainly focused on the building simulation technology, including the building physics, like Professor Kang just mentioned. And also, it's our great honor that Professor Kang is our editorial board members of our journal, and also have published one review paper for the acoustic modeling issues. We're very thankful for Professor Kang's great support to our journal, and also welcome everybody to submit the papers to our journal and have a more suggestion to how we can make this journal more popular and more easily to affect with our society. So that's all for my presentation. Thank you, everybody. Thank you very much.
Okay, thanks very much for Professor Da Yan's informative talk. So I wonder if there's any question from our audience. Okay, so I would like to have a very general question, Professor Yan. So I think nowadays everyone talks about big data, but I think in the building related studies, usually we feel that the so-called big data in our era is not really big or not big enough. So I wonder, in your opinion, that because you are using the occupant profile to do the building energy studies, so at least how many data sets, or what is the resolution when collecting data do you think is enough to reflect the reality?
Yeah, thank you, Professor Chao, for it's a very tough question. Not easy to reflect, but I try my best to answer this or reflect this. That's the big data. We also we like to say big data, but sometimes compared with some other area, our data is not so big enough. We say big enough and also not diverse enough. But I think there's two concepts. One is using the machine learning approach to do the data analysis. That's so I think one very promising area. But this area we need to closely connect with our physical understanding and also knowledge. Sometimes this is very effective to improve the accuracy of the model and very easily to use for the real application. That is one kind of advantage if we're using the machine learning model. The second, if we look at the big data part, the big data, from my point of view, big data, one part is the data, which is you have a very big volume of data. Another very important concept is try to convert different types of data together. For instance, we have the data for the occupancy. We have the data from the climate. We also have the data from the electricity usage. So we can merge the three types of data together. We can find quite a lot of the very different phenomena or characteristic compared with our original or conventional approach. That is sometimes we say, from my point of view, it's a big data. It's give us a lot of potential to do it in the future. So it's still a long way to go, but if we got some new new advanced, and then more and more data will be achieved in our field. So that is some brief thinking for the big data. Please feel free to drop your comments for this. Yeah, that's for our brief discussion. Thank you.
Thank you, Professor Yan. And any other audience would like to raise your question to Professor Yan? So, so Professor Yan, I wonder the approach you introduced in your lecture. I wonder, is it applicable for both public buildings or commercial buildings, and also residential buildings? Because as I understand that maybe in public buildings there are more people, and maybe most of the people have similar behavior patterns. But in like residential buildings, there are large individual differences. Maybe the situation would be more complex. So, so I just don't know. I would like to ask you.
Yeah, you are absolutely right. If you compare with the residential building and also commercial building, the electricity use profile is much easily to easily to forecasting and to generate in the commercial building compared with in the residential building. Because the behavior issue in the residential building is so significant, because different families have a different timetable for the daily usage. So the electricity has been driven by these daily activities. So it's very diverse between the different families. But this kind of data or phenomena is also changed based on the different scales of the building we are focused. For instance, if we look at one room or one household, electricity usage is so diverse and so stochastic process. And if you look at the whole district, very big district, because people's behaviors, although is very different or diverse from each other, but they will convert to a very stable total electricity usage in a residential district. So if we look at one district residential buildings electricity usage, that is much easier to compare to forecasting compared with the single families electricity usage. So that is one kind of this transaction between the different space and different time resolution. So I think it is still quite a lot of different angles to do this modeling issues. So that is one quick thinking for the really quick response to your very important question. Yeah, thank you, Professor Chao.
Thank you, Professor Yan. Well, I think it's almost time for almost dinner time for people in Beijing, and the lunchtime for people in UK. So I think we have to close Professor Yan's talk. And if you have any other question, you could contact Professor Yan through email.